Okay, hello everyone. Let's go ahead and take a look at what are called related rates. Okay, now let's just go ahead and take a look at two different equations that are related, but obviously have some very apparent differences. Here is the area of a circle, and we all know that that's going to be pi r squared. And then we have the derivative of the area of the circle with respect to time is equal to pi times it by 2r times it by d of r over d of t. Now, what we want to go ahead and take a look at is that this right over here doesn't have any differentiation applied to it. So what we're going to call that is we're going to call that a static equation. So in other words, if we go ahead and substitute a particular value of r into this particular formula here, we can find out the area of a circle given that value of r. But when we go ahead and take a look at this, and notice that what's happened is I've taken the derivative of both sides with respect to t. So notice that the derivative of the area of the circle with respect to t is just this, and pi of course is just a constant. If I go ahead and take the derivative of r squared with respect to t, that's 2r times it by d of r over d of t. So look at what happens now is that we're now talking about this particular equation which involves two different rates of change. This rate of change here and that rate of change there, as well as the value, a particular value of r. We are now going to call this a dynamic equation, because what we're looking at now is we're looking at how these rates of change are related, which is the reason why this whole section is called related rates. Okay, it's actually related rates of change. Okay, so what we have then is we start off with a static equation. We take the derivative with respect to t of both sides, and we come up with a dynamic equation, which is how the rates of change are related. So the key concept then is that all related rate problems involve differentiation with respect to time. Okay, so let's just go ahead and take a look at an example here. We have a function that says y is equal to x squared minus 1 for x is greater than or equal to 0. Okay, and we're going to say that if x changes at a rate of 1 unit per second, what is the rate of change of y for different values of x? Okay, so let's just kind of get a conceptual idea of what's happening here. The static equation is y is equal to x squared minus 1, which is basically just the graph itself. But if we were to go ahead and consider what's happening here, if x changes at a rate of 1 unit per second. So let's say for every second it's just going to go like this, like that. Okay, that's what's happening to the x value. What exactly is happening to the y value? So in other words, if I go one value over here, how quickly is that, at that point, how quickly is the y value changing? We know that this is going to be changing at a constant rate. How quickly is this changing? And that's what we can actually go ahead and do using calculus and using the dynamic equation. So let's go ahead and approach this. We know that the static equation, or the static initial statement, is just the equation itself of y is equal to x squared minus 1. Now notice it says that if x changes at a rate of 1 unit per second, that's a given. It's telling you basically that d of x over d of t, or the rate of change of x with respect to t, is just 1 unit per second. Okay, now what we have now is the static equation and the givens. If we go ahead and take a look at the static equation and differentiate with respect to t, again what we come out with is a dynamic equation which relates the rates of change. So d of y over d of t is going to be equal to 2x times it by d of x over d of t. Of course, the constant will just disappear because if we take the derivative of a constant, it will go to 0. So what I can do now is I know that from the given, the change of rate of x with respect to t is 1 unit per second. So this right here can become 1. And now I know that the rate of change of y with respect to t is always going to be equal to 2x. So now let's go ahead and take a look at what the rate of change of y with respect to t is for different values of x. So when x is equal to 0, okay, when x is equal to 0, we're talking about that point right over there. d of y over d of t is going to be 2 times 0, which is 0, which means that there is no change of rate at that particular point for that particular instant, even though x is changing at a rate of 1 unit per second, and that makes sense because it's at the minimum, and the rate of change at that point is 0. Now, if we go ahead and take a look when x is equal to 1 though, so what happened then is that we jumped over here, okay? We're taking a look at the value of the rate of change of y at this particular moment. Remember that x is moving constantly like this now. Y is going like this, it's getting faster and faster and faster. So what this is saying then is that when x is equal to 1, the change of y with respect to t is going to be 2 units per second at that particular instant. Okay? And then when x is equal to 2, d of y over d of t is equal to 2 times 2, which is 4. And notice, of course, the rate of change of y with respect to t is getting faster, which is true because we know we're dealing with a quadratic function. Okay, so let's go ahead and kind of wrap all of this up again. What are the primary differences that we want to go ahead and take a look at for this particular section is, can we actually come up with a static equation, and can we go ahead and make sure to determine what the particular givens are for the particular questions that you're looking at. Second, if you go ahead and you start off with the static equation, can you go ahead and differentiate with respect to t to come up with the dynamic equation? If you can do that, then of course what you're doing is you're looking at the related rates, or you're relating the rates of change through the dynamic equation, and then you can go ahead and solve for particular rates of change. Okay, so that's a very simple example. Some of the other questions that you'll come across with in the textbook will be a little bit more challenging, but we'll go ahead and take a look at those in class. And one other thing that I would like you to do is make sure to go ahead and take a look at the demos on the website. What it does is it shows you how certain values are changing based upon movement, of course, because we're talking about related rates. And of course, sometimes it's sometimes easier to see how certain things are changing when you can actually see the movement involved. So go ahead and take a look at the demos on the website. Hopefully everybody has an understanding now of where we're headed to with regards to related rates, and we'll take a look at those questions the next time that we have class together. Okay, so give it your best shot, and I'll see you later. Bye-bye.